Hello, and welcome to the tutorial for galvanic cells, which is part of Big Idea 3. So galvanic cells naturally come after single replacement reactions, and these are also sometimes called voltaic cells, and they're batteries because they produce voltage or electricity. And if we remember seeing single replacement reactions and we saw that E cell value, we said, well, single replacement's all we need to know if it's positive or it's negative, because if it's positive, it happens. And if it's negative, E cell value, then the reaction doesn't happen when you mix the chemicals together. In this case, we actually care what the voltage is because we're actually going to produce that amount of electricity. And the simple cells that we're going to be dealing with, there are way more complicated galvanic cells, but the simple ones that we're going to start out with are just single replacement reactions with the oxidation reduction half reactions taking place in separate containers. So the containers are connected to one another through a salt bridge and a wire, but the reaction materials will be in individual components, individual sections. So let's take a look at an example set up. And I'm going to clear this so that we have room. Okay, so let's take a look at this first example. When you're given a galvanic cell, sometimes they actually tell you what's happening at the oxidation and the reduction, or you have to figure it out. But let's start with the most simple ones. And in these cases, you're going to be given two metal electrodes, in this case copper and aluminum, and then you're going to be given solutions, which oftentimes what we'll notice here is like the copper goes with the copper 2+ and aluminum goes with the aluminum 3+. They go together, and we'll see why in just a second. And so when you look at this, we're going to draw the setup really quickly here, and I'm going to redraw this a little bit better later on, but just to kind of give you an idea of what's going on. So instead of having one beaker and you dump everything in, you're going to have two separate beakers. And one of these, an oxidation is going to happen and one's a reduction. We don't know which way yet because we don't have enough information. So there's going to be a salt bridge, and I'll explain that later. So that's what's connecting the two. And then you're also going to have a wire that's going to connect the two pieces of metal. And this is just so that the reaction can actually occur. Because obviously, if there's nothing connecting the two of them, then you can't have a reaction. So in a single replacement reaction, you have a metal, you add it into a solution, it either reacts or it doesn't react. In this case, you're going to have a metal on this side, so this is going to be your copper, and this is going to be your aluminum. And each one is sitting in a solution. So this one's sitting in a copper 2+ solution, and this is sitting, and there are spectator ions. I'll draw those in later, but for right now, we don't need them. And so you have available the ions and you have the metal. So what we need to figure out is which one of these is getting oxidized and which one is getting reduced, because we have the ions for both and we have the metal for both. So we're going to have to set up two competing possibilities. All right, so now we have some workspace. So you're basically going to set up two possible potential reactions, and one's going to work and one's not going to work. So what you're going to say is, well, maybe it's possible that what's getting oxidized is the copper. Well, if copper is getting oxidized, that means it's going from the metal to the 2+, and it's giving up 2 electrons. And the electrons. All right, so I think it cut out a little bit there. So 2 electrons. So just like in a single replacement reaction, we're going to look this up on the table, and when we find it, it says positive 0.34, but we're going to make this negative because it's an oxidation reaction, and those are always written as reduction. So it's very similar to what we do in a single replacement reaction. So if the copper is getting oxidized, the metal is becoming the ion, then the aluminum reduction would go from the ion. So the key thing when you're doing this is The one needs to go from the metal to the ion, and then the other one needs to go from the ion to the metal. So in this case, you would have aluminum 3 plus, and that would pick up 3 electrons, and that would go to aluminum metal. So that would be getting reduced. And we look that up on the table. We don't flip the sign since it's a reduction, and it's a reduction table. And when we add this up, we are going to get negative 2.0 volts. So, this is a negative number. And what we know about negative numbers is this reaction is not going to happen on its own. And so what this basically tells us is we don't have this going the right way. And the reason why you're able to flip these over, and I'll explain what that means in a second, is because we don't just have copper. We don't just have aluminum in solution. We also have copper, and copper 2 plus, right, the ion, and we have aluminum. So you have both the metal and the metal ion because they're in solution together. And so what it basically means is either the copper can get oxidized or the copper can get reduced. Either the aluminum can get oxidized or it can be reduced. Just one pair has to get oxidized and one pair has to get reduced. So let's do this over, but this time we have to flip it around. So instead of the copper getting oxidized, since that didn't work last time, we're going to try it with the copper getting reduced. So we're going to do, whoops, actually, I want to list this as oxidation first. It doesn't really matter. You can, what did I just do? Okay, so put this back. All right, so I just want to list, it's fine to list the reduction first. I just am trying to keep it consistent. So this time, instead of the copper getting oxidized, the aluminum is getting oxidized. And notice here, when I start with aluminum, I'm not starting with the aluminum 3 plus, because in order for this to get oxidized, it has to go from the metal to the metal ion. It has to lose electrons. And again, I can do that because in this case, I have aluminum and I have aluminum 3 plus. So I can choose to start with whichever one I want. Now, when I put this over here, this is going to become positive 1.66 because on the table it's listed as negative. And then reduced would obviously have to be the copper. So now copper 2 plus is getting reduced to copper metal. And that would be positive because when I look it up, that's its value on the table. And that when we don't flip, so this would give us 2.0 volts, and that would be our E cell value. Okay, so we've now tried both out. When copper was oxidized and aluminum was reduced, it did not work. So we're going to give this one the big cross out. It kind of reminds me a little bit of oxidation, of limiting reagent problems, where we tried both out and one way works and one way doesn't work. The only difference with this is if we had done this one first with the aluminum getting oxidized and the copper 2 plus getting reduced, and seeing that it has a positive voltage, you don't really have to do it the other way around, because once you get a positive voltage, you know that's your right direction. So since this one down here at the bottom is right, we need to make the electrons cancel out just like a single replacement reaction. And so we're going to multiply this one through by 2, 2, and then this becomes 6. And down here we're going to multiply it by 3, so then this one also becomes 6. And we can add these two half reactions to get our overall net. So we have 2Al plus 3Cu 2 plus. Gives us 2Al 3 plus 3Cu. Okay, so this is our overall net. This is our net reaction, just like a single replacement reaction. And this is going to be our standard reduction. So this is how much voltage I will produce if, and let's remember what standard is, all the solutions are 1 molar, which may not be true, but this is what you'll get if you have exactly 1 molar solutions. So this would be of the aluminum chloride and of the copper sulfate. Both have to be 1 molar. It has to be at 25 degrees Celsius, and it has to be at 1 atm of pressure. That's what the little standard, this little circle-y thing up here means, okay? And we'll talk about how it can deviate from that once we finish to draw out this cell. Okay, so I am going to erase all of this, okay, so that we can go back and look at this in the actual beakers. All right, so I've redrawn the actual setup. So let's just kind of go through all of the components. So here's our reaction. I rewrote it over here, the net ionic. That was our voltage, our E cell value. All right, so this basically is going to be a beaker full of solution of copper 2 sulfate. And inside of here is this actual physical piece of copper. So that's going to be metal. And this is going to be connected to a wire. So there'll be a little alligator clip here. And that is going to be connected through here. Oftentimes you'll see this, it'll say voltmeter, and this is optional. This just reads the voltage. Otherwise, the wire would just keep going through. Either way is acceptable. And that's going to connect over to here. And again, there's going to be a little clip, and you're going to be connected to a piece of aluminum metal. And that's in a solution of aluminum 3+ and chloride. So this aluminum and the sulfate, they're both spectators, so we don't really worry about them. They're just kind of hanging out in the solution. All right, so let's talk about what's really going on here. But how we understand what's going on has to be based on this chemical reaction. That's super critical. So let's look at what the reaction is telling us. The reaction is telling us that these things on the reactant side, these are getting used up because they're reactants, and these will be produced. And what sometimes confuses people about these galvanic cells are that, well, we already have aluminum 3+, it's right here, and we already have copper metal, it's already right here. So how can it be that we're producing something that we already have? And that can be a little bit tricky. So the reason why we start with aluminum 3+ and copper, you actually don't need them. You could replace them with other things, is that if you put a different chemical in here, so you don't need copper metal to be this electrode. So I'm drawing it right here. You don't need this to be made of copper. You could have it be made of another metal. But if you put some other metal in with copper 2+ solution, you run the risk that another reaction will happen, one that you don't intend. If you put copper with copper 2+, you eliminate that. These two aren't going to interact with one another. Same thing over here with aluminum. You need the aluminum metal because that's a reactant. We need to use that up. And if I was to put that into a solution containing some other type of ion, it would be possible that they could react. So this just eliminates that issue. But you can actually create these cells without copper metal and without aluminum 3+ because they're not needed as reactants. So, all right, so what is happening here is that this aluminum over here, so the two things we do need, I'm going to highlight them in white. So the two things we really do need here are the aluminum, because what's going to happen is this cell runs, is the aluminum's going to shrink. The aluminum metal is going to turn into more aluminum 3+. So I draw these arrows. And what those arrows are showing me is that I am reducing the mass of the aluminum. Well, where is that mass going to? It's increasing the concentration, the molarity of the aluminum 3+, because what does our reaction tell us? It tells us that the aluminum is getting transformed into aluminum 3+. It's getting oxidized. So this over here, this cell, is our oxidation cell, and oxidation cells are known as anodes. Okay, and if we come over to here, on this side, the copper 2+, the copper is staying exactly where it is. On top of this electrode, more copper will plate on top. So this electrode, we call the metals the electrodes. On top of this electrode, we will have an increase of mass. So there actually will be a plating of copper on top. So the mass of the copper will increase. And as this cell runs, there will be a decrease in molarity of the copper 2+, because again, that's getting used up in the reaction. And these arrows here are indicating to us the reduction reaction that's happening, that the copper 2+ is turning into copper metal. And it just happens to cling to the metal because that's where the electron transfer takes place. So since this is the reduction side, we call this the cathode. And there are a couple ways you can remember this, which side is which. So a lot of people remember anox, so anox for anode oxidation, and red cat for the cathode being the reduction. You can also look at it this way. These are both vowels, and over here R and C are both consonants, and so they kind of go together. So whichever way helps you to remember. So now we understand what's going on. Let's figure out where these electrons are, because that's super important as well. Okay, so now I'm going to look at what's happening with the electrons. So over here at the anode, because that's where oxidation takes place, electrons are being produced. And those electrons that are being produced, instead of them just being transferred right in the solution, they're being moved through this wire. And that's why we actually are able to capture the voltage, because we have electrons moving through this wire. And then the electrons are coming to this side where they're picked up by the copper 2+ and turned into copper metal. So they're being lost over here on this side. That's what this arrow is showing us as it becomes aluminum 3+, and they're being gained over here by the copper 2+ to turn into copper metal. And so these arrows here are the movement. Wow, we have a lot written on here. The movement of the electrons. All right, basically we have two last things to talk about. The next one is going to be explaining the salt bridge. So this right here. So the purpose of the salt bridge is if you have electrons moving through here, you're going to end up with a buildup. If you don't have anything to mitigate it, you're going to have a buildup of negative charge on this side. And if you have a buildup of a charge, if you remember anything from physics, the circuit won't be complete and it will stop running. So a salt bridge completes this circuit by allowing those charges to rebalance. So we look over here, what are we losing? We're losing a whole bunch of copper 2+. Well, what does that mean we need? Well, we need to replenish plus charges. And so a salt bridge will just, again, be a paper towel soaked. It can be as simple as a paper towel soaked in salt water. And so the cation from the salt will move over to here, and that will replenish those positive charges. It's not replacing the copper 2+. It's just allowing positive ions to move into the solution to replenish that positive charge that's lost by the copper 2+. If we come over to the anode side, we're not losing positive, we're gaining the aluminum 3+. That's actually building up. So in order to balance that out, we are going to move over the chloride ion, and that will balance out those extra aluminum ions that are produced. And that explains the salt bridge. So labeling the salt bridge is never enough. You have to describe where the ions are traveling. And an easy way to remember it is the cation will go towards the cathode and the anion will always go towards the anode. But it's good to understand why that's occurring as well. The final thing that we have to talk about is the voltage. So if you make perfect solutions, they're each 1 molar, brand new, right? Put them in solution, you should produce exactly 2 volts of electricity. Of course, that's in an ideal situation. What happens is as you run this cell, so you run this galvanic cell, the molarity of your copper 2+ is going to go down because you're using it up, right? That's a reactant, so it's going to decrease. And the amount of aluminum 3+ is going to increase. And what this basically is going to do is as this runs, your voltage will drop. So over time, your voltage decreases. And that will actually happen anytime you increase the concentration at the anode or you decrease concentration at the cathode. So let's say you have a different setup here. So let's say you don't start with 1 molar solution. Let's say that you start with the copper 2+ as some of your copper sulfate. Let's say you start with that as a 2 molar solution. And you would start with the aluminum 3+, which is, remember, the one that we actually don't even need. And let's just say you start that one out as 1 molar. So because this one, the one that we actually need in the reactant, is higher than the aluminum, which is the one that's in the product, that will increase the voltage. So you actually get an increased voltage here. Well, what if we started it out the opposite way? So let's take this away, back this up a little bit here. And let's say that you started with this as 1 molar, and you increase this to 2 molar. So this is kind of the opposite, right? So you have more of what's in the product than you have in the reactants. And when you have that, so you have to look at the ratio. It's not necessarily that you're increasing one or the other, it's the proportion to each other. So if you have more products than you have reactants, that's going to decrease your voltage. So this will read decrease voltage. So this will actually be less than 2 volts. And there's an equation that you can use called the Nernst equation to actually solve how much this is, but you aren't required to do that for AP. So that's in your book. I'm happy to show you also if you want to be able to actually set it up and solve for it. But anytime you have more of whichever one is in the product, whichever solution is in the product, than the one you have in the reactant, that will decrease your voltage under the standard value. Let's look at one last example. What if you set it up and you created both of them? And then I'm going to back this up for a second here. It's the easiest way to do this. Okay. Let's say if we set these both up to be 0.5 molar. So now they're not standard solutions, but they're both equal to each other. This actually will go right back to the same E cell value that we initially had, because again, why? Neither one is more than the other initially, and therefore that will keep that proportion the same, which keeps your E cell value the same. And if you increase them both to 2 molar, it would do the same thing. As long as the proportion is the same, the voltage will remain constant. In this case, your battery will have less time at that 2 volt voltage than if they were 1 molar. But that's, you still will, for that immediate calculation, have 2 volts. And if you think about this logically, this is basically what happens in your battery. If you start with a 9-volt battery, it's only truly 9 volts. So that's like the square batteries that you get, rectangular batteries. They're only 9 volts the very first second that you plug them in. Once you start using them, the voltage drops because you're using up that energy. You're increasing the ions that are produced at the anode, and you're decreasing, right? You're removing them from your cathode, and that's going to drop your voltage. So this is the end of the first tutorial. I'm going to do a second example problem, and the third example problem will be with acid, which is really important to watch. So look forward to those next videos.